So we've been working on finding derivatives. A derivative is basically just a function that tells you the slope of the graph of another function at any point. Remember, our idea was to, we called it f prime of x, or the change in f with respect to x. This little d stands for a tiny difference in f and a tiny difference in x, so that's what the d is for. We were calculating that based on this limit. We were going to find the slope of the secant line, which is f of x plus h minus f of x all over h. This is the change in f over the change in x. And we're going to take the limit as h goes to 0. So we're finding from the average rate of change over some small interval, that's the slope of the secant, we get the instantaneous rate of change, which is the slope of the tangent. Well, the point is that the derivative is based on some kind of limit, right? It's some sort of limit procedure that you apply to a function. For about 100 years after Newton, even though calculus was having great success at describing what was going on in the world around them, there are people that still didn't really accept calculus or thought something was a little bit fishy. And they had a good point, because they would say, well, what's happening here is h goes to 0, obviously. You have nothing divided by nothing. How can that be something? So it seemed a little bit weird that you could have something coming from 0 divided by 0. So one of the critics, I think his name was George Berkeley, he said derivatives are ghosts of departed quantities. These two quantities, the numerator and denominator, have somehow disappeared, and yet something was left over. He was just kind of making fun of how it seemed somewhat ridiculous. Now the issue is really just understanding what a limit is. You can think about this as being some function that depends on, in this case, h primarily, because that's the variable that we're changing, although it also depends on another variable, x, and we're just finding the limit as h tends to 0 of that particular function. So the issue really revolves around what does any limit mean? If I say the limit as the input approaches some value c of the output is some value L, what does that mean? And as I said, it took about 100 years after Newton for a good definition to be obtained. So what came out was the epsilon delta definition of the limit. And once they had a good definition, once mathematicians have a good definition, they can use that definition to think logically about it to draw conclusions. So we're going to come up with the epsilon delta definition of the limit much later on in this class. So for now, just kind of our usual hand-waving approach to limits is going to be just fine to get us through. When we get to the end, though, we'll come back and kind of do it in the order that it was actually done and look at this epsilon delta definition of the limit. Right now, though, it would be nice to know about some of the properties of the limits that you can prove once you have that epsilon delta definition. So that's what I want to talk about right now, are just basic properties of limits. Now, they'll be pretty obvious, and the point is just to say we can kind of use this definition to come up with some systematic things that if we ever start to get lost, we'll have something that we'll be able to go back to, some principles that we know always are true. So let's look at those properties here. The first two are the sum and difference rules, and they should be pretty obvious. We have this function f, and as the input gets closer and closer to c, the output of f gets closer and closer to L. And we can also assume that for this function g, as the input gets closer and closer to that same value c, the output of g is getting closer and closer to m. So if we build a new function by adding those two functions, the sum rule just says, well, the limit would be what you expect. If f is getting close to L and g is getting close to m, then the combined function should be getting close to L plus m. Now, we've used that a lot here. What if we wanted to find the limit as x tends to 3 of, maybe x plus 4x? Right? We can see this first part, if x gets close to 3, this is just going to get close to 3, right? And as x gets close to 3, 4 times the number really close to 3 will be really close to 12. And so those, if you build some function by adding those two things, then you're going to get the sum as the limit, right? If that's getting close to 3 and that's getting close to 12, then together they'll get close to 15. And it's really obvious. It's just sort of a systematic statement. It's something that you can prove once you have the definition of limits. Same thing, if you take the difference of those two, then that should get closer and closer to the difference of those two limits. So we could sum those up by saying the limit of the sum is the sum of the limits, the limit of the difference is the difference of the limits. We could even write both of these rules in one combined statement. We just say the limit as x tends to c of f of x plus or minus g of x, you choose what you want to do, is just equal to the limit of f plus or minus the limit of g. Okay. Here are a couple more that should be pretty clear. If you have these two functions f and g, and f is getting close to L and g is getting close to m, then their product should get close to L times m. After all, a number close to L times a number close to m ought to be close to L times m. So that's just the product rule for limits. So you say the limit of the product is the product of the limits. So we would say here constants come through limits, because if you have this function f, it's getting close to L, then if you take k times a number that's closer and closer to L, you ought to be getting closer and closer to k times L, right? K times a number close to L ought to be pretty close to k times L. So that's the idea there. We would say that constants come through limits. Multiplied what was I trying to write? Constants come through limits. Good. Two more. A quotient rule. If f is getting close to L and g is getting close to m, then as long as m isn't 0, you would think that if you divide those two numbers, you should get closer and closer to the quotient of those two. So to say it in words, the limit of the quotient is the quotient of the limits. Good. And power rule. All right. So you can prove from that limit definition that if you have two integers here and you're making some fractional power, maybe this integer is 1, and so you're just talking about a regular power, like maybe r is 2 and s is 1, you're just talking about f of x squared. But you could also do something like maybe 1/2, so a fractional power like 2/3. All of those would work. So the limit of the power is the power of the limit. Okay, so let's say we've got something like this. We know that x is approaching 3, and we're looking at x squared. Then we know x is getting closer and closer to 3, so what we can do is just figure out what is x getting closer to and square it. Of course, if x gets closer and closer to 3, this gets closer and closer to 3, so we have 3 squared, and that's 9. So these statements are all pretty obvious. Again, we're saying them in a systematic way so that we can think about, okay, what do we know is true, and we can work through it slowly. Let me show you an example of doing that. Okay, here we have three functions, h, p, and r, and we each have their respective limits as the input approaches 1. So when x goes to 1, h goes to 5. When x goes to 1, p gets closer and closer to 1. When x goes to 1, r gets closer and closer to 2. And what we want to do is to find this limit, this interesting combination. We want to do it systematically and just name the rules that we use as we go through step by step. So I recopied it here, and let's just say what rule we're using at each step. Now the first thing I notice is that we have one function, maybe a little complicated here, divided by another function, and that gives me a hint that I could use the quotient rule. So I'm going to take the limit as x tends to 1 of the square root of 5 times h of x, and divide by the limit as x tends to 1 of p of x, 4 minus r of x. And what I've done is to apply the quotient rule. So I'll just label this so everyone can see what rule I'm using, right? The quotient rule for limits. We're going to have rules for derivatives pretty soon, and they're going to be, some will be the same, but some will be quite different, and so I'll just write for limits to make it clear that we're talking about rules for limits in this case. Okay, so the limit of the quotient is the quotient of the limits. That's what we mean. Now technically there was something we had to check with that, right? It required this limit to exist, and also required this limit to exist and not be 0 in order for these two things to be the same. We're just going to move forward trusting that that's the case. But if we were to find out that this limit actually was 0, we'd have to go back and rethink what we were doing just a little bit more carefully. Let's assume that they exist and then apply the principles. If it turns out that they don't exist in the end, then we'll rethink, but everything should be pretty safe. Next thing you might notice is that the square root of 5 times h of x is the same thing as 5 times h of x to the 1/2. And so if you're taking the limit of some power, some rational power like 1/2, then you know the limit could go inside. So what we can do in our next step is write this as the limit as x tends to 1 of 5 times h of x to the 1/2 all over the limit as x tends to 1 of the product of p of x and 4 minus r of x. Good, so all I've done is basically bring the limit in underneath the square root, because after all the square root is just a power, and the limit of the power is the power of the limit. Alright, next step on simplifying this limit, I notice that I have a constant times a function, so I could just pull that constant through, right? Constants come through the limits, so I'm going to rewrite this. At this point, you're probably getting somewhat bored. In fact, you may have already arrived at the answer just by thinking about it, right? 5 times something close to 5 would be 25, and the square root of 25 is 5. So the top has got to be getting closer and closer to 5. Down here, p is getting close to 1, and r is getting close to 2. 4 minus something close to 2 should be close to 2, so we have 1 times 2 down below. So we know the answer is going to be 5/2, but I just want to point out that when we do that, we're actually just using these limit laws in maybe a sort of sloppy way. So usually it works out okay, but sometimes we get a little bit lost, and if we could fall back on what we know to be true, that would be pretty safe. So here's our power rule for limits. That's what we've... Oh no, what have we done? We've done at this stage we did the power rule for limits. And at this stage we did the constant multiple rule, right? I'll just write constant mult rule for limits. I haven't done too much with this limit downstairs at all. I've been sort of saving it. Okay. Well, now we're pretty good with the top, because we know that we know what the limit as x tends to 1 of h is. We know that's 5 because that was given to us. So now we have up on top, we have 5 times 5 to the 1/2. Alright, now, down below, we have the limit of a product of two functions. And we know from the product rule for limits that that's the limit of the product. So the limit as x tends to 1 of p of x times the limit as x tends to 1 of 4 minus r of x. So what we've done here is to do a little bit of substitution and to apply the product rule for limits. Alright, let's see. So up on top, if you take 25 and find its square root, that's just going to be 5. And down here, we know that the limit as x tends to 1 of p of x, we're told that that's 1, so we might as well just substitute that in. And then this last one, that's the limit of a difference. We have the limit as x tends to 1 of 4 minus the limit as x tends to 1 of r of x. So we have 5 over 1. So what we've done here is to use the difference rule and a little substitution, because we knew what the limit of p of x was. So difference rule for limits. And let's see, the limit is x tends to 1 of 4. Well, 4 is always 4. It doesn't care what x is, so that limit's going to be 4. And the limit is x tends to 1 of r of x. We're told that that limit was 2. So just put those in, and just a little bit of arithmetic here. 4 minus 2 is 2. We get the limit as 5/2. Now here's a problem that I'd like you to try on your own. In this case, we're given what the limit of the complicated thing is. What we want to do is just find what's the limit as x tends to 7 of f of x. So our idea is to use limit laws to try to get within this expression the limit of f of x alone. then we'll be able to solve for that quantity. So why don't you give that a try, and then I'll have the solution in the next video.